comes in this data set right away. In this case, it's the dog versus the cat pictures. Because there are a lot of dog pictures and only one cat picture in this case. I emphasize that with the colors. So, what's the, this is big or small, Marco?
Small.
And it turns out this guy is the biggest number. So what's the eigenvalue of this set of this matrix? What are the two eigen? What's the maximum eigenvalue? What's the minimum eigenvalue?
The maximum is A.
And the minimum is Z. So A over Z gives you a very poor condition number, meaning you're going to have these ellipses to deal with. Another way of looking at the ill conditioning of this set of equations is just look at the geometry associated with this type of misfit function. Again, you have all these residuals that are red associated with the dogs, and only one of the residual, this predicted minus the observed, is only one of those guys. This is very small because units are very small. Units because the dog picture is taken at night. And there's so many of these other cat pictures. When you try to find a solution, it's going to pay attention to reducing the residual associated with the reds, not the green. And that's the whole point. You want to distinguish cats from dogs in this neural network. So when you train the neural network, if it's not going to pay attention to the dog too much, it's going to, it's not going to pay attention to the cats. I guess this is a cat. Then it's going to probably label everything as a dog when you train it. You can make that mistake. And then say, well, I don't care. I only made one little mistake. That doesn't count much in my total misfit function. So what are you going to do to fix this problem, Marco? What?
I can reduce the dimension.
Reduce the dimension?
Yes.
What does that mean?
Take all the lesion values that give me the more meaning.
Well, one thing you could do is change the units for the cats. The cat picture is taken at night. So what you can do is, you can do a histogram stretch if you've heard of that before. Do any photoshopping. You can take that 0 to 55 bunch of numbers and multiply them by 5, and now you've taken the range from 0 to 55 and brought it out to the range of 0 to 200 and greater than 250. So now the cat picture looks pretty bright. So at least you now kind of have the same units as these guys. And in the travel time tomography example, in one case, the travel times might be in milliseconds. The other case, for the red, might be in seconds. Well, the numbers for the coefficients here are going to be dramatically different. So you want to change the units so everybody has the same units. So one way to do that is to take all the cat pictures, or all the dog pictures, take all the values associated with the dog pictures, a squared plus b squared in the matrix, and then divide through by the first equation by that guy. Second equation, you do the same thing. In other words, you're normalizing the values of the matrix coefficients on the first row, on the second row, on the third row, by the total sum of the squared values there with the square root. What that does is, the units of this might be, say, kilometers. Well, the units of 1 over that is what? A squared square root is going to be kilometers. So you're getting rid of the units right away. And for your cat pictures that are green, you do a similar type of exercise. And we're going to see more detail about this later on. So in other words, you're turning the values of each of these rows here so that now the diagonal components are about the same size. And that's called scaling. So you turn that set of ellipses associated with the original set of equations into a round concentric circles. Any questions on that? There's another trick, and we're going to find out about that in another couple of slides. We also demean the input values. And what do we mean by demeaning? Looking at?
Dividing or moving the mean point of x. I mean, like dividing the x values by their mean, so that we give them less weightage.
Okay, so you have all these points here. And meaning that you take the sum of all these vectors and divide by the number of vectors, and then that's called the mean vector. Let's call this the mean vector of that. And so every point here gets demeaned by subtracting from it the mean of the cloud here to give you the new input. And I'll tell you why we do that in a minute. So this is another way in which we get better solutions, is not only just normalizing the set of our matrix, each of the rows in our matrix, but also demeaning them. And then finally, the third remedy that we're going to find out in neural networks is we want to balance out the data types. We would not have had this problem if we only had one picture of a cat, right, Marco? How many cat pictures do we need to get an equal number of rows here of green that would give us an equal number of residuals that are green?
The same number of them.
Yeah, it's called balancing the input data set. So these are the three cures you're going to need for your neural network or your convolutional neural network. And I'm just kind of wondering, the guy who asked me that question in class, if he had that kind of experience or knowledge of how to fix problems before they begin. And those are the three standard methods that we use to fix problems. You balance the number of cat pictures, the number of dog pictures. And if you have 20 categories of pictures, you got to make sure all 20 types of input pictures you have are the same. Not only the same, but also the same size. Got it? And I'll give you a geometric interpretation of what that means. Because there's so few of the greens out here, and according to this guy, this only has a very small, it has a direction, but it's very small length. These guys, there's a lot of them. So when you add up a lot of these dog residuals, dog gradients, well, they're going to add up to something that's really long. It'll be some direction, but they'll add up to something very long. So you're not trying to find the solution to things associated with the cats at all. Okay, I'm going to mainly try to...
Why you cannot simply normalize by the number of... divide the number of picture of dog you have?
Say again?
In the last formula, why the red part, the transpose of x multiplied by the dy, I cannot simply normalize by the number of the total picture of dog that I...
You can do that too. That's one way of doing it. But the standard ways are these three things. You get out of trouble by making sure everything's balanced. Then you make sure your units are the same. Because the green, like I said, the red inputs could have very different units than the green inputs. And I use the example of cats, pictures taken at night. It has the same units, but you can think of lots of other examples. Okay, bias term. Why did we demean things? Well, let me give you an example. This is my motorcycle in Utah, and this is the Great Salt Lake, and it's very interesting out there. You can watch for snakes and scorpions. And let's think of us doing some time trials along this road here. We have clocks. And we have someone judging where you are, that is, along this road here, straight road, and how long it took you to get there. So you do a time trial, and they give you they have a person there, and they clock you what time you get there. And notice it's not exactly a straight line because some parts of the road are kind of mushy because of the rain from the previous day, so you can't go as fast. Not only have to make errors. So your modeling equation, if you're not thinking about it, should have done something like this, but it didn't. And why didn't you include the bias term? Well, you're from the old days. You think, just a matrix vector, multiply will be good enough. And that doesn't include a bias term typically. So you think, you have a linear relationship between inputs and outputs. You think, just a matrix vector multiply will do it. So you implicitly ignore what we call a bias term. Let me tell you the danger of ignoring that. Okay. Here's our system of equations. Notice we have the starting time at 0 at the location x equals 0. And then 1 kilometer away we have this time. 2 kilometers away we have that time, 3, and so on. And so this would be, if this is a distance times something will give you time, and that something must be slow, so it's the inverse of velocity. So we go ahead and set this up into a general set of system equations using x rather than the actual numbers. And we go ahead and use our least squares procedure. And by the way, that's an inconsistent set of equations. You already know the answer. Our starting point is to get a data misfit function, and we go ahead and then find the gradient, and then we get an answer, and we get a good slope. But if it turns out that our original experiment was such that the timing clocks did not start, I did not start at time t equal to 0 and x equal to 0. I started at a different time. Therefore, if I didn't include this bias term, I'm going to have some crazy line like this to fit this. This could be inadequate. Why? Because I did not use a general enough system of equations to relate the inputs to the outputs. So to fix this problem, we need to turn the system of equations to include also an unknown bias term, B. Not just W, but B. How do I do that? So if I have an unknown bias term, and I have M1 here, and I have X1, T1, that's first equation. T2 is equal to B plus X21. So how do I represent this in terms of matrix vector algebra, like I have over there? What's my new matrix X?
X11.
What's my new? What are my new unknowns? Before I had the unknown. I'll call that W1. Okay, my previous unknown was just W1. Now I have another unknown, B. Okay? The coefficients for the vector B. So what are the coefficients? Okay, so we have here W1. Let me just B W1.